Hello everyone. In our previous class, we discussed about the optical properties of semiconductor and also differentiated between interband and intraband absorption process. While studying that, we understood that electronic properties are more significant when compared with the optical lattice properties when you concerned with the practical application. So that's why our discussion will be concentrating on the opto-electronic absorption process. So first let us see what are the different types of opto-electronic absorption. So one thing we need to remember is under this we are having two terms, that is opto and electronic. Opto means it is related to optics, means light is involved. Light is made up of photons. So what happens here, there is the involvement of photon, and as I explained while explaining the optical property, so because of the involvement of photon we are going to study the properties of the semiconductor. So here in optoelectronic absorption process, a photon will be involved, and when it is incident on a semiconducting sample, then we know that semiconductor is made up of valence band as well as conduction band. These are nothing but electronic bands. So there will be some changes or transition of the carriers, and based on that we are going to classify different types of optoelectronic absorption process. So opto is related to involvement of photon, and electronic is defined with respect to the electronic bands of semiconductor, which is valence band and conduction band. So mainly there are four types of transitions or absorption process under this. First one is the fundamental absorption process. Second one is exciton absorption process. Third one is the free carrier absorption. And fourth one is absorption due to impurities. So let us see in detail one by one. Today we are going to deal with the first type, which is the fundamental absorption process. So fundamental, it means very basic. So this type of process is found in all the semiconductors, we can say. So it is a basic and most important process in case of semiconductors, and it involves the transition of electrons from valence band to the conduction band, and because of its importance this process is referred as fundamental absorption. So if you consider the band diagram, it is nothing but energy versus wave vector diagram. We have E is equals to h cross square k square divided by 2m star, which means that E is directly proportional to square of the wave vector. That's why we have parabolic nature of the electronic bands. So at the lower energy we have the valence band, which is inverted parabola, and at higher energy we have a conduction band. So we have already studied that valence band consists of a number of electrons, and when a photon is incident on the semiconductor, the photon which carries some energy, that will be absorbed by the electron which is present in the valence band, and the energy of the electron will be increased, and it is going to transit or excite to the higher energy band, which is the conduction band. So here we can observe that the electron from the valence band is transited to the conduction band. So transition is in between two different bands, and that's why we call it as interband transition, and the absorption is interband absorption. So when this transition takes place, after transition the excited electron which is present in the conduction band is free to move. Means it is acting like a conduction electron which contributes for electrical conductivity. and because of this transition a hole will be created in the valence band, and that one is also free to move. So these are acting as a carriers in case of semiconductors. So from this only we can understand more and more absorption, which is fundamental absorption, takes place. More and more free carriers will be created, which means that electrical conductivity is going on increasing for this type of absorption process. So that is secondary. With respect to practical application, let us concentrate on the fundamental absorption process. So what is the condition for the absorption to take place? We have a photon with energy h nu, and the energy gap, that is the energy difference between the top of the valence band and the bottom of the conduction band, that is the minimum energy difference, that is nothing but your energy gap. So there should be some condition for fundamental absorption to take place, and the condition is that the photon energy h nu should be greater than or equal to Eg, that is the energy gap. And if the photon energy is less than the energy gap, it means fundamental transition or absorption cannot take place, because along y-axis we are having energy. So electron which is present in the valence band, it is having its own energy, and if it has to overcome the barrier, that is forbidden gap, and go into the conduction band, then it needs energy equal to the energy gap. And when it acquires that much energy, then only transition is possible. That's why that energy will be supplied by the incident photon, and if the energy of the photon is equal or greater than that of the energy gap, then only the electron from valence band can excite to the conduction band. So for fundamental absorption to take place, this is a required condition. So from this condition we can say that frequency should be greater than or equal to Eg by h, and when Eg by h is equals to nu, that is frequency of the photon is equal to Eg by h, then it is called as absorption edge. That is where the absorption just starts. So the significance of this will be discussed later. So in the transition process, that is nothing but the photon absorption process, some conservation laws are to be conserved. Means the total energy as well as momentum of electron-photon system must be conserved. So let us see what all terms are conserved, and based on that what conclusions we can make up. So if you consider the total energy, means the energy of the electron before transition, let it be Ei, and Ef will be the energy after transition, that is energy of electron in the conduction band, and h nu is the energy of the photon which is incident on it. So when you see this, conservation means the energy before transition should be equal to after transition, but here Ef is not equal to Ei. Ef is equal to Ei plus h nu, that is final energy is equals to initial energy plus the photon energy. So we can see that here energy is not actually conserved. Then coming to the momentum. Momentum is nothing but h cross into k. So if I just omit that h cross, we can explain with respect to the wave vector, so that it will be easy to interpret in our band diagram, as it is a E versus K diagram. So the final wave vector will be equal to initial wave vector plus the wave vector of incident photon. And the wave vector of incident photon is negligibly small in optical region. And that's why Q can be just neglected, and finally we get Kf is equals to Ki, that is the wave vector of electron in the conduction band will be equal to wave vector of electron in the valence band. Therefore we say that momentum of electron alone is conserved, but energy is not conserved. So this selection rule says that only vertical transitions of electron in K space is allowed. There won't be any crosswise transition possible. So let us understand it properly. So if you consider again the band diagram, that is nothing but E versus K diagram. Energy is not conserved. So along y-axis the transition may be equal to Eg, greater than Eg, or very much greater than Eg. It is immaterial. But when you compare the x-axis, which is the wave vector which gives us the momentum, we have Kf is equals to Ki. Kf is with respect to conduction band, that is the final wave vector, and Ki is with respect to the electron in the valence band. So Kf should be equal to Ki means that the transition of electron will be only straightwise. If it is crossed, it means that K is changing. That is, the wave vector will change, which is not true according to the conservation of momentum. That's why we say that for fundamental transition, only vertical transition in K space is allowed. Then let us see about the absorption coefficient so that we can interpret more significance. So from quantum perturbation theory technique, we have the absorption coefficient which is of the form alpha d is equals to E into square root of h nu minus Eg. A is a constant which involves the properties of the band. So we can say that alpha d is directly proportional to square root of h nu minus Eg. So that we can say that alpha d, which is the absorption coefficient for direct band gap semiconductor. Direct band gap means the top of the valence band and bottom of the conduction band exist at same K value. So alpha d, which is the direct band gap absorption coefficient, increases parabolically with frequency nu above the fundamental edge, because at fundamental edge you can say that h nu will be equal to Eg. So it will be equal to 0. Alpha d is 0. But after the fundamental edge, alpha d increases parabolically with respect to frequency nu. So let us understand by plotting a graph of alpha d as a function of photon energy h nu. Then according to this equation, we get a parabolic graph as seen. And the absorption starts when h nu, that is the photon energy, is equal to the energy gap of the semiconductor, and this is called as absorption edge, or also called as fundamental edge. So what is the significance of this fundamental absorption edge? So by knowing the fundamental edge, we can measure the energy gap of a given semiconductor. We know that energy gap of any semiconductor is a characteristic parameter of that semiconductor. If I just say energy gap of a given semiconductor is 1.1 electron volt, then easily you can say that the semiconductor given is a silicon. That's why energy gap plays a very important role when you come under semiconductor physics. And that energy gap can be measured by using this optical method, which is the fundamental absorption process. So when h nu is equals to h nu naught, that is nothing but when h nu will be equal to Eg, that is the energy gap, the absorption will just start. And if you note down the frequency where the absorption just starts, that value will be nothing but your energy gap, or that value gives you the energy gap. So if you find out what is nu naught, h nu naught will be equal to Eg. So based on the absorption H, easily we can find out the energy gap of semiconductor, and that is a very important significance of this fundamental absorption edge. So then if you find out the order of the direct band gap absorption coefficient, then it comes up to 10 raised to 4 per centimeter. And as you can see, the order is large. We can say that the absorption is readily observed even in the thin samples. There is no need of a very huge sample or a large sample. Even if the sample is small, absorption coefficient is going to be larger. So studies are going to be very easy. So if you consider the conductivity experiment, where we will just find out what is the conductivity of the sample with respect to temperature and all, and we plot a graph where we get a negative sloped graph, and if you take the slope will be equal to Eg by 2 kb, and if you substitute, finally you will get what is the value of Eg. But in that case, for conductivity experiment, you need to take a larger sample. But if you are having a lesser sample or in a small quantity, then optical method is very significant to measure energy gap. So this is the main importance of studying fundamental absorption process. So nowadays optical methods are preferred for finding out the energy gap of any semiconductor. Then this is about direct band gap semiconductor. So here energy gap of semiconductor, we know that it ranges from 0.1 to 5 electron volt, or we can say lesser than 5 electron volt, and that energy gap is very less, and the corresponding frequency when you find out, that is Eg is equals to h nu, then nu will be equal to Eg by h. When you calculate for any general value, let us say Eg is 4 electron volt or 2 electron volt, then if you divide by h, that is the Planck's constant, you get the frequency of the order 10 raised to 13 hertz generally. And that's why we say that the fundamental edge usually occurs in IR region, that is the infrared region, because the frequency 10 raised to 13 hertz is coming under the infrared region of the electromagnetic spectrum. And that's why the study of IR region of the spectrum has been greatly expanded by the semiconductor research, like for example infrared detectors. So we can understand the practical importance of this. And the absorption process occurs in direct band gap semiconductors is what we have studied from the selection rule, that is Kf should be equal to Ki, and that is possible only for direct band gap semiconductors. and the examples are gallium arsenide, indium antimony, etc. So if you take an example of gallium arsenide and plot a graph of absorption coefficient as a function of photon energy h nu, you can observe a graph which is similar to that of the characteristic graph which we have seen. That is, at different temperatures we can study, but the nature is going to remain the same. So absorption will start at certain energy and then will have the same nature. So this is about the fundamental absorption in case of direct band gap semiconductor. But as I told you, fundamental absorption is a very basic type of absorption process which occurs in semiconductors. But according to the selection rules and conservation laws, we studied that only direct band gap semiconductors will show the fundamental absorption. But is it true? Actually not. Even in indirect band gap semiconductors, we can observe this fundamental absorption. But how? In these type of semiconductors, electrons cannot make the direct transition from the top of the valence band to the bottom of the conduction band, because it violates the momentum selection rule, which is Kf is equals to Ki. That is, if you consider the band diagram for indirect band gap semiconductors, the tips of the bands are not one below the other. That is nothing but the definition of indirect band gap semiconductor. And that's why direct transition of electron from valence band to conduction band is not at all possible according to the selection rule Kf is equals to Ki. Then what has to happen now? Because fundamental absorption will take place, but the transition will take place in two steps. So first there will be involvement of photon and then phonon simultaneously. So when a photon is incident on the semiconductor, that energy will be absorbed and photon supplies the needed energy and will do transition in the y-axis, that is one above the other, because Kf should be equal to Ki. But the extra momentum which is required for the electron to get into the conduction band will be supplied by the phonon. So phonon involvement is present, which gives the extra momentum, and in this way, that is in two-step process, fundamental absorption will take place in case of indirect band gap semiconductor. So based on this, again we can define indirect band gap semiconductor absorption coefficient, that is given as alpha I is equals to A dash of t into h nu minus Eg whole square. So here we can observe that alpha I is directly proportional to h nu minus Eg whole square. So if you plot a graph of alpha as a function of photon energy h nu for indirect band gap semiconductor, let us consider germanium, because germanium as well as silicon are the examples for indirect band gap semiconductors. So the graph is something like this at different temperatures, and here we can observe the nature where there are two steps involved. One is with respect to photon and with respect to phonon. So it is something like doubling the first graph, that is in case of direct band gap semiconductor. So at two different temperatures, nature remains the same. So as we can see that the dependence is to the square of h nu minus Eg. This variation will be much faster when compared to alpha d. That is, alpha d varies as h nu minus Eg to the power of 1 by 2, and here it is to the power of 2, that is the square of it. So here variation in alpha I is rapid when compared to alpha d. That is, if you say h nu minus Eg is equals to 2, then alpha I will be proportional to 2 square, which is 4, whereas alpha d will be proportional to square root of 2, which is 1.414. In that way, based on the variation, if the variation is rapid, then we can say that the semiconducting sample which we have taken is indirect band gap semiconductor, and if the variation is slow, that is with respect to square root of the function, then we say that the semiconductor is direct band gap semiconductor. So this process helps us to distinguish between direct band gap semiconductor as well as indirect band gap semiconductor. So this is another use or significance of first type of optoelectronic process, which is fundamental absorption. Then second is, already we have seen, it helps in determination of energy gap, and when once you determine the energy gap, easily you can say which semiconductor it is. So these two basic properties or basic property of a semiconductor can be determined by studying the fundamental absorption, and main thing is that the optical method is an improvement over the conductivity method. So for optical method you need not take a large sample, even a smaller sample is enough, and the process is very simple when compared to the conductivity method. So in conductivity method you need to find out different parameters and then finally tell about the basic properties of semiconductor. But when compared to the optical method, where you are just incidenting some photons on the semiconductor and output is studied, and based on the output easily you can find out different parameters or properties of semiconductor. So this is about the first type of transition or the fundamental absorption process, and in my next class we will be studying about the exciton absorption process. Thank you.